Hello everybody, you're going to be doing Lewis dot structures along with the bonding that you did yesterday and the day before together, okay? Okay, so let's say you have carbon and hydrogen. Carbon is a nonmetal and hydrogen is a nonmetal, so this would be a covalent bond, okay? Now, carbon has 1, 2, 3, 4 valence electrons. Hydrogen has 1 valence electron. Now, like you learned yesterday and the day before, if you have a covalent bond, those electrons are going to share. So, that means you're going to have a bond between the carbon and the hydrogen, and they are both sharing hydrogen. Electron and carbon's electron. So now same thing with the other hydrogen over here. Carbon and hydrogen are going to share. Hydrogen, now remember, for hydrogen to be stable, it has to have 2 valence electrons. For carbon to be stable, it has 8 valence electrons. Okay, so here hydrogen is sharing that electron with carbon, so therefore carbon has 2 electrons. It is now stable. Now here carbon, you've got 2, 4, 6, 8 valence electrons, so now carbon is stable as well, okay, because it has all 8 valence electrons, or at least it's sharing 4 of them. Okay, this is a covalent bond, and this is your Lewis dot structure. Okay, now here you have oxygen, which is a non-metal, and you also have hydrogen, which is a non-metal. So a non-metal plus a non-metal gives you a covalent bond. Oh, goodness gracious. Now remember, that means that they're going to share. I ran out of space over here. Okay, so this structure is your bent. Okay, so now, is it going to be the hydrogen that's pushing towards the oxygen, or is it going to be the oxygen that's pulling on the hydrogen and the hydrogen, or is it going to be the hydrogen pulling away from the oxygen? Now that is coming from your electron negativity, which is, we talked about that during the trends. Okay, oxygen's going to have a higher electron negativity, so the oxygen's going to actually be pulling the hydrogens around. And that's going to be a polar bond because it's an unequal pull. Okay, now some people say, ma'am, how can I tell when I'm drawing the structure? Because here you have 1, 2, 3, 4, 5, 6 valence electrons for oxygen. Then hydrogen, let's do that in red, is 1 valence electron and 1 valence electron. So now remember, because it's covalent, they're going to share on that bond. Every time you have a bond, you have 1 valence electron on one side and the other valence electron on the other. So if it's covalent, they're sharing. If it's ionic, one is transferring. So here you're sharing. But you see how you had an open space here and you had an open space here? That's how you know where your bond goes. And that means this is bent. It's your bent shape. And this is your valence electron structure for water. Okay, now I always get asked, ma'am, do I have to figure out the valence electrons to be able to do the Lewis dot structures? Well, not really. You can also do it with the oxidation number. So remember, on your periodic table, you're going to label, and I think that was on the notes yesterday or the day before, the top of your periodic table. So if you have one, write down these charges on top, because it's going to help you for the rest of the year. So that first group is going to have a +1 oxidation number. Your oxidation number is your charge. The second group, your earth metals, are a +2. Your boron family is a +3. Your carbon family is a ±4. Your nitrogen family is a -3. Your oxygen family is a -2. Okay, and fluorine is a -1. Your halogens are 0. And let me make that a little darker in case it's hard to read. So fluorine's a -1, that whole group. -2 for the oxygen group. -3 for that nitrogen group. ±4 for carbon group. +3 for that boron group. A +2 for this beryllium group, the earth metals. And a +1 for your alkali metals. Now, I always get asked, ma'am, is that going to change my type of bond? Yes. So if I have something like a potassium, which is K, that has a 1 valence electron. So now you can count from left to right. It's the first box, so you have 1 valence electron. Or you can look at the charge on top. Anytime you have a plus charge, this is going to be lost. You're going to lose that electron. So let's say we get something like sulfur. Sulfur has a valence of 6, or it's right here, and you have a -2 charge. A -2, what does that mean? It means it can gain 2 valence electrons. So sulfur, your valence electrons are 1, 2, 3, 4, 5, 6. That means you're missing 2 valence electrons, and that's why it can gain 2 valence electrons. Okay, so now let's put that in there. 1, 2, 3, 4, 5, and 6. So because potassium is a metal, remember this is your metal side, everything below the stairs, over here, are your metals. Everything above the stairs, these are your non-metals. Okay, and I ran out of space. Okay, so because I have a metal and a non-metal, this is going to be an ionic bond. So because it's ionic, they're going to transfer electrons. So that means this valence electron is going to transfer into this empty space, and this bond right here, Ks, is your chemical compound. Oh, wait, there's another empty space. Let's go back. Just saw that right there. You see how there's an empty space right here? Well, sulfur's not satisfied because it doesn't have all 8. Here by this transferred electron, it has 7, right? Because it's stealing, or the K is transferring to sulfur. So now instead of sulfur having 6 electrons, it has 7. But because we still have an empty space, now remember, when you have an ionic bond, one's going to be the giver, the other one's going to be the taker. And since potassium has a +1, it's going to be the giver. And since sulfur only needs 2, it's going to be the taker. So potassium is going to transfer into that empty space. So basically your chemical compound is KSK. And that is your Lewis dot structure. Okay, now if we need any more help with either ionic or covalent Lewis dot structures, let me know. Go ahead and start the Lewis dot structure and oxidation number practice and ask me for help.